Hello, in this video I'd like to talk about titration curves. We have been studying titration reactions. For example, the titration of an acid indicated by HX with a strong base like sodium hydroxide. This reaction produces water and the sodium salt of the conjugate base, X-. HX could be a strong acid or weak acid. Or we could study the titration of a base indicated by the neutral formula B with a strong acid such as hydrochloric acid to form the conjugate acid of the base BH plus Cl minus. In each of these cases, the acid or base that we're starting with, HX or B, is the analyte, the substance that we are titrating. The strong base or strong acid, sodium hydroxide or hydrochloric acid, is called the titrant, the stuff we're adding. A titration curve is essentially a graph of pH as a function of volume of titrant added. So at zero volume, we have a solution that contains just the analyte, either the acid HX or the base B. The titrant, sodium hydroxide or hydrochloric acid, is added, its volume increases, and then we measure and graph the pH throughout the addition. So here are the things that you should be able to do. Number one, for a given titration curve, explain why the pH varies as it does for both types of titrations, and explain exactly what's going on in all regions of the graph. Meaning, what are the most important species present at that particular point in the titration, and why is the pH what it is? Second, use the measured pH at various points in the titration to calculate Ka or Kb for the analyte. Finally, for the given initial conditions, meaning volume and concentration of both analyte and titrant, calculate the pH at any point in the titration. So, let's look at some examples. In our first example, which we are doing in our lab experiment, we are titrating nitric acid with sodium hydroxide. Nitric acid is a strong acid. It reacts completely with sodium hydroxide to form, of course, water plus a solution of the conjugate base, aqueous sodium nitrate. And as we saw in the laboratory, this is what our titration curve looks like. We have volume of sodium hydroxide in milliliters added on the x-axis, and we have pH on the y-axis. Okay, so we start at a very low pH. So at volume 0, when we've not added any sodium hydroxide, the pH is about between 1 and 2, as we would expect for a concentration of a strong acid. And for much of the titration, the pH remains very low. That's because nitric acid is present in great excess. However, as the moles of sodium hydroxide added begin to approach the moles of nitric acid we start with, we see that the pH begins to change very, very rapidly. We see a very, very rapid increase, and you notice that there is what's called an inflection point, the point where the pH is changing most rapidly. That corresponds to what's called the equivalence point. The equivalence point, the point of inflection, is when the moles of sodium hydroxide we've added are equal to the initial moles of nitric acid present. Okay? And let me write that down. I think that's important enough for us to have in the notes. Okay? So, the equivalence point is the point of inflection, which we see on the graph in the green dot. And that means that moles of hydroxide added equals the moles of nitric acid we started with. Now, if you ask yourself, what is the pH at the equivalence point, we see, interestingly enough, that the pH is equal to 7.00. At the equivalence point in the titration of a strong acid with a strong base, the pH is neutral. So why would that be? Well, we're going to ask ourselves the question that I'm going to ask you literally 10,000 times this unit, which is, what is the major species present at the equivalence point? Well, in this case, the two major species present are the sodium cation and the nitrate anion. Well, as we know, nitrate is the conjugate base of a strong acid, which means that it is non-basic. So of course we have a neutral solution. So how do we figure out the volume of sodium hydroxide titrant required to reach the equivalence point? Well, as you will see or have saw in our lab, we use a spreadsheet to calculate the change in pH for each data point and the equivalence point is where we have the maximum change in pH. As we said before, the equivalence point is the inflection point. That is where the pH is changing most rapidly, and we can use a spreadsheet to determine that. Now, what about titration of a strong base with a strong acid? This, for example, would be starting with sodium hydroxide as our analyte and adding, let's say, for example, hydrochloric acid, a strong acid, as our titrant. Well, obviously, this forms water plus sodium chloride. Again, the major species present at the equivalence point is going to be sodium chloride. Chloride, being the conjugate base of a strong acid, is non-basic. Therefore, we would also expect a neutral solution. Well, this is pretty much what the titration curve looks like. And as you can see, it is very similar to the titration curve for titrating a strong acid with a strong base. It's simply flipped upside down. We start at high pH. The pH remains level for a long period of time. As we approach the equivalence point, the pH begins changing rapidly. The inflection point, i.e. the equivalence point, is where the pH is changing fastest. That corresponds to a pH of 7. And that is because the major species present at the equivalence point are the sodium cation and the chloride anion, which are completely non-basic. Now, what about titration of acetic acid with sodium hydroxide? Here's the equation. Acetic acid plus sodium hydroxide reacts to form water plus sodium acetate, the sodium salt of the acetate anion, the conjugate base of acetic acid. What we see, and what you will see in the lab if you haven't already done so, is something that looks somewhat different. Here's where the pH varies with volume of sodium hydroxide. So a couple of things that we see different. First of all, the initial pH is much higher, and it's between 2 and 3. That makes sense because if we have a solution of acetic acid, a weak acid, it's going to have an initially higher pH. Okay? We also see that the pH rises fairly rapidly and then kind of levels off in the middle part of this titration curve. We also have an inflection point up here where the pH is changing most rapidly. And again, the inflection point is the equivalence point when the moles of sodium hydroxide we've added are equal to the moles of acetic acid we began with. But now you see something very different. If you move over to the y-axis, the pH axis, you can see now that the pH at the equivalence point is greater than 7. At the equivalence point in this titration, we do not have a neutral solution like we did before. We actually have a basic solution. Why is that? Well, once again, ask yourself, what are the most important species present at the equivalence point? And they are, of course, the sodium cation and the acetate anion. So, why is the pH at the equivalence point greater than 7? Well, we have, as I said before, these two ionic species present in highest concentration. Now, we have the conjugate base of a weak acid, which is a stronger base than water. And the most important equilibrium that's established is the weak base ionization of acetate in water, governed by kV of acetate, to form an equilibrium concentration of acetate and the hydroxide anion. Because the hydroxide anion is produced in greater concentration than the neutral water, the pH is going to be greater than 7. So we have a basic solution. Now, what about the titration of a weak base with a strong acid? So for example, let's say that we're titrating ammonia with some strong acid, for example, hydrochloric acid, to form a solution of ammonium chloride. Oops, let me fix that. Well, what we see is pretty much the inverse of the previous graph. We start with a solution that contains only ammonia, so our pH is quite high, around 11. Again, we see a quick drop-off, a leveling, And then as the pH begins to change very rapidly at the equivalence point, we have a pH now that is less than 7.00. Why would that be? Once again, ask yourself, what's the most important species present at the equivalence point? In this titration, it would be the ammonium cation plus the chloride anion. And as we know, the ammonium cation, being the conjugate acid of a weak base, is a stronger acid than water. It ionizes to form ammonia plus the hydrogen ion. And again, it's the presence of the hydrogen ion in greater concentration than that formed in neutral water that forms a solution with a pH less than 7. Okay, now, here's a really important point. What is the significance of what's called the half titration point? The half titration point is, the half titration point in a titration is defined as the point when you have added half the titrants needed to reach the equivalence point. Meaning whatever you're starting with, whatever the analyte is you're beginning with, you have reacted exactly half of it. Okay? Well, that is defined, as I said right there, the point at which you've added half the volume of sodium hydroxide needed to reach the equivalence point. What that means is that half of the acid has been neutralized. So for example, if I consider the titration of acetic acid with strong base to form water plus the acetate anion, as written here, if I write out my Ka expression, Ka is equal to the hydrogen ion concentration times the acetate concentration divided by the concentration of acetic acid. Well, if at the half titration point, half of the acid has been neutralized, what that means is that at that point, the remaining concentration of unionized acetic acid is equal to the concentration of acetate anion we have produced. If those concentrations are equal to each other, then they simply cancel. And what I find is the half titration point is the point at which the hydrogen ion concentration is equal to Ka, or taking the base 10 negative logarithm, pH is equal to pKa. Okay? So to annotate this graph, here again is the equivalence point, where our most important species present is the acetate anion. If I take that volume, which on this graph looks like it's about 24, divide it by 2, go to about here, this would be equal to the half titration point. Okay? And again, at this point, the concentration of acetic acid that remains is equal to the concentration of acetate anion that I've produced. pH is equal to pKa. You will also notice that this is the center of the plateau on the graph, which we call the buffer region. The buffer region is the area centered on the half titration point where the pH is changing most slowly. So, what is a buffer or a buffered solution? A buffer is defined as a solution that contains an acid-base conjugate pair, again, which means either a weak acid and its conjugate base or a weak base and its conjugate acid. But remember, we're not using those terms anymore. It's an acid-base conjugate pair, and they are in similar concentrations. At the half titration point, they're in equal concentrations, but within the buffer region, they are close to each other within an order of magnitude. So why is this significant? Well, a buffer is a buffer because it resists change in pH when you add strong acid or strong base. And that's really important. How does it do that? Well, it can do that because it contains both the acidic and basic components. So if I add excess strong acid, then the basic component neutralizes it to form more of HA. On the other hand, if I add strong base, then the acidic component neutralizes it to form some of the conjugate base plus water. The fact that it contains both the acidic and basic components means that it can neutralize either strong acid or strong base when it is added. Okay? And as I said before, the plateau in the titration curve is the region where the concentrations of the acidic component and the basic component are similar to each other, so that, as I've shown in the blue parentheses there, is the region of maximum buffering. And we'll talk more about buffers later in this unit. to summarize, this is what the titration curves of a weak acid and a strong acid look like. What you notice is that the pH of the strong acid solution starts much lower. It remains fairly low for much of the titration. It begins to rise rapidly. And at the inflection point, or the equivalence point, the pH is equal to 7. On the other hand, the weak acid starts at a much higher pH because it's a weak acid. Quick initial increase, levels off, forming a buffer zone. When we reach the point of inflection, that is the equivalence point, way up here, we see that the pH is greater than 7.00. So these are the main differences in the titration curves of a weak and strong acid with strong base. Now, one of the points that I made earlier on is that one of the things you can do is calculate the pH at any point in a titration, starting with the initial volume and concentration of the analyte, meaning the stuff that we're titrating, and the added volume and concentration of the titrant, the stuff we're titrating with. We'll calculate, in this order, the moles of analyte initially present, using moles equals molarity times volume. The moles of titrant added at that particular point, also using moles equals molarity times volume. We will then calculate the new concentrations of all species that are formed after the reaction is complete, using stoichiometry. And then we will calculate the resulting concentration of hydrogen ion or hydroxide, and therefore the pH, using equilibrium. So in these problems, calculating the pH at any point in a titration, it is a two-step process. First, you perform a stoichiometry calculation, then you perform an equilibrium calculation. So let's do finally an example of one of the most important of these types of problems, which is calculation of the pH at the equivalence point in a titration. We want to know what that pH is here at the equivalence point in the titration of a, for example, weak acid with strong base, and you'll see why that's important in the next section. So, question is, what is the pH at the equivalence point in the titration of a weak acid with a strong base? For example, a student titrated 35.0 milliliters of 0.775 molar acetic acid, for which Ka is given, with 0.625 molar potassium hydroxide. Calculate the pH at the equivalence point. So here are our important questions. Number one, what is the chemical equation for the titration reaction? You need to know what reaction is taking place while you're titrating. B, what is the major species present at the equivalence point? We talked about this, but you have to explicitly think what is formed at that point of inflection. And then finally, what equilibrium is established at the equivalence point? What exactly is going on? And for that, you should be able to write a chemical equation, the equilibrium expression, and the K value. Well, let's do this for this particular problem. So, when we're titrating acetic acid with potassium hydroxide, we form, of course, water plus potassium acetate, the conjugate base of acetic acid. I've left off physical states here, but you know that they're all aqueous or liquid. Okay? What is the major species present at the equivalence point? Again, it is the conjugate base of the weak acid we titrated. The most important species present at the equivalence point in this titration is the acetate anion. That's going to determine the pH. And what equilibrium is established? Clearly, the weak base ionization of acetate to form acetic acid plus the hydroxide anion. That's what makes it basic. Fix that formula there. What is the equilibrium expression? Kb is equal to the concentration of acetic acid times the concentration of hydroxide divided by the concentration of acetate anion. Well, that's simply equal to Kw over Ka for acetic acid, which we're given. Okay, so here's our roadmap for this process. We begin by calculating the moles of weak acid initially present. From that, we can calculate the moles of conjugate base formed at the equivalence point. From that, we can calculate the concentration of the conjugate base at the equivalence point, from which we can calculate the pH. So here is our procedure. We begin by calculating the moles of weak acid initially present, using moles equals molarity times volume. Now, because the reaction here in A is a 1-to-1-to-1 stoichiometry, that means the moles of weak acid initially present are equal to the moles of hydroxide we need to add, and also equal to the moles of the conjugate base present at the equivalence point, 1:1:1 stoichiometry. Once we've done that, we calculate the volume of titrant potassium hydroxide solution needed to reach the equivalence point, volume equals moles over molarity, and then finally, we calculate the concentration of the conjugate base at the equivalence point. Actually, not finally, that's step 3, using molarity equals moles over volume. And then, in the final step, using the Kb expression for the conjugate base, calculate the hydroxide concentration, and from that, the pH. So, let's do this. In step 1, we will calculate the moles of acetic acid initially present, 0.775 moles per liter times the volume, 0.0350 liters, is 0.0271 moles of acetic acid, but that's also equal to 0.0271 moles of potassium hydroxide needed, and also equal to 0.0271 moles of acetate, the conjugate base, at the equivalence point. So, what volume of potassium hydroxide solution do we need? Well, we simply take the moles required, calculated in step 1, 0.0271 moles of hydroxide, divide that by the molarity you're given, 0.625 moles per liter, or 0.0434 liters of potassium hydroxide solution. In step 3, to calculate the concentration of the conjugate base acetate at the equivalence point, we'll use concentration equals moles over volume. That would be 0.0271 moles of acetate divided by the total volume of solution present at the equivalence point, which is equal to the initial volume of analytes plus the volume of titrant added, which we calculated in step 2, to give me 0.347 moles per liter of the conjugate base. Let's box the important results here. Okay, that, and that. So now in the final step, now that we know the concentration of acetate produced at the equivalence point, we can calculate the concentration of hydroxide and the pH. Here is the equation representing the ionization that occurs at the equivalence point. I can write my Kb expression. That is equal to x squared over the initial concentration of acetate calculated in step 3 minus x. What's that Kb numerically equal to? Why, of course, it's equal to Kw divided by Ka for acetic acid, or 5.6 times 10 to the negative 10th. That's a pretty small Kb value, so I'm going to assume the simplifying approximation is valid. Thus, x is equal to the concentration of hydroxide produced at the equivalence point, which is equal to the square root of the product of the concentration of hydroxide times Kb, or 1.4 times 10 to the negative 5th molar as my hydroxide ion concentration. And that's consistent with our expectation that the solution be basic at the equivalence point. That concentration of hydroxide is greater than that of neutral water, therefore we have a basic solution. And then finally, in the last step, the pH of the solution at the equivalence point is 14.00 minus the base 10 logarithm of the hydroxide ion concentration. Sorry, that's 10 to the negative 5th, not 15th, is equal to 9.14. Again, completely consistent with our expectation that in the titration of a weak base with a weak acid with a strong base, the pH at the equivalence point is greater than 7. In the next section, we'll talk about why that's important. See you then.